Start. Start. Very good morning to you one and all. I am D.C.Chennaiah, Head of the Mechanical Engineering Department, DBSIT, KAVALI, SPSR, Nellore District, Andhra Pradesh, India. Today I would like to discuss the present scenario of power generation, energy business with the gas turbine technologies. Next slide, please. The first slide, how Elk City generated at a gas-fired power plant. As already we know very well about the different forms of energies available, but the supreme form of energy is electrical energy. Whatever the types of input source of energy they may be available, but our main aim is to convert that all input energies into the supreme form of electrical energy. So here we're discussing the electrical energy generation by using a gas-fired power plant. Within the gas turbine, it's called as the heart of the power plant. The combustion gas reaches the 1500 degrees centigrade, hot enough to melt some metals. But by using certain cooling techniques, we will protect the life of certain metals. The hot gases reaches through the turbine, setting the special alloy turbine blades in rotation at a speed of over 3000 RPM. This rotational energy is converted into electricity by the power generator fixed on the end of the turbine shaft. MHI, this MHI means Mitsubishi Heavy Industries. It has a benchmark in production of G series gas turbine, which generates around 330 megawatts of power, which is sufficient to provide the electricity of 40,000 homes. Once in operation, our turbines are expected to constantly provide electricity, hence they need to show ultimate toughness and reliability. This gas here, next slide please. Here, let us see the two nodes. The combustion gas exceeds 1500 degrees centigrade in G series gas turbine, which is MHI's core product, and 1600 degrees centigrade in the J series gas turbine, the world highest inlet temperature. Here G series, J series gas turbines, we are hearing the term. They are the certain manufacturing codes, D series, F series, J series, K series, like that. Depending upon the rotational speed, the number of stages, and the production power, they will manufacturers given this catalog to these gas turbines. The highest temperature now we are reaching the temperature of 16 degrees centigrade in the J series gas turbines. This is the gaseous temperature which may have the inlet to the turbine before entering to the gas turbine. When using the 50 Hz 701 G series turbine, the calculator is based on the household of 4 people and using 2 kilowatts. In the last slide, we discussed 40,000 of people or homes. Understand? In each home, we are expecting 4 people presented. The 40,000 into 2 kilowatt. If we calculated them, we can have the picture of production of electricity by using this 701 G series gas turbines. Above rotor, the rotating part of the gas turbine is under construction, which consists of several stalk ring-shaped parts. Subsequently, an operation of attaching the turbine blades will follow. Takasago Machinery Works, this is Japan-based company. Hugyo Perfection is producing such type of gas turbines. Next slide, please. Let us see this in ingenious skills that overwhelm the world-class skills reflecting technique and monodoscopy. Here we are seeing the different monodoscopy. This is the Japanese term. What the meaning of this term means? To product or to manufacture or to making of, like that. So here there are skills overwhelmed worldwide, reflecting the techniques, especially in the gas turbine field. Although renewable energy power generation has recently attracted attention, thermal power generation, which has long been supporting power supply, is also making tremendous progress in efficiency. Here we are talking about the renewable energy sources. Available energy sources are two types. One is conventional energy sources and non-conventional energy sources. Non-conventional energy sources are called as renewable energy sources. Year by year, season by season, day by day, the energy will be renewed by the universe. That is why we are calling them as renewable energy sources. As the cost utilization of conventional energy sources or fossil fuels, they will be depleted by one day. So the coming generations will be faced with such a problem regarding the sources of energies. That is why world keep on creating the awareness among the people worldwide to best utilization of the renewable energy sources. In the such situations are also this gas turbines, especially thermal power generation. It has its own importance, and it is attracting the people concentration which can be used for generating the electrical energy. Perhaps the most prominent example is the J series gas turbine, which achieved an inlet temperature in the 16 degrees C class. The 16 degrees is the temperature of the gases before in entering the gas turbine. Such higher temperatures we are achieving. So if a gaseous substance is having such a higher temperature, means the gases will also have higher value of the enthalpies. So this hot gases is made to flow through the nozzle. This nozzle converts that entire enthalpy drop into the velocity and as well as the kinetic energy. With that high kinetic energy, the gases strikes the turbine blades, and these gases will expand over the turbine blades. So they produce certain rotational work, and these blades are mounted on the rotor. Therefore, turbine will rotate. The turbine will be keyed to the shaft. So the shaft rotates. From this shaft, this power will be transmitted to the generator, and hence the electricity will be generated. So J series turbine can be applied to gas turbine combined cycle power generation that conducts secondary power generation by the steam turbine, utilizing the exhaust heat expelled after rotating the gas turbine. So by using these gas turbines, we can make it as a primary generating system or secondary generating system. Here, after production of power or after expansion of the gases over the turbine blades, still that gases are having enormous amount of heat. So unless otherwise the setup of secondary power generation, these hot gases have to be uselessly discharged into the atmosphere. Because of this, they causes the loss of heat and causes the decrease in economy, and also it causes the increase in global warming, and also it creates certain environmental pollution also. So by using this heat, we can produce the best power with help of secondary power generation. So here in combined cycle, we are attaching one duct to the turbine exhaust. So that exhaust gases after doing the work, this will end to the certain steam generator where water will be heated up and the formation of steam takes places, and the produced steam will runs the steam turbine, and hence again power is generating. So because of this combined cycle, we are getting very much higher thermal efficiency, 60%. In actual case, it is alone gas turbine unit or steam turbine unit never generated as 60%. But once we have the combination of these two, we are able to get 60% of thermal efficiency, and also generating the power of 460 megawatt. Here, how we are getting that much higher efficiency, 60%. That means thermal efficiency is nothing but the ratio of work output to the heat supply. Here, we are supplying the heat to the gases, as we are supplying the fuel to the compressed air, which may react with the oxygen and come up the combustion process, heat will be generated. For that only we are supplying the fuel, but same generated heat we are using in the secondary cycle also. That is why we are getting the power output. The first power output from gas turbine, and second power output from steam turbine. So thermal efficiency, total power output by the uh, Supplied heat. The supplied heat is same. That is why we are getting a higher thermal efficiency and generating power of 460 megawatts. This accomplishment, which paves the way for the new applications in the field of thermal power generation, would have been impossible without the ceaseless efforts to research technology coupled with abundant experience. Still, there are certain researchers keep on going to improve the turbine inlet temperature 1600 degrees centigrade to 700 degrees, 1800, 20 to 2000, like that. Researchers have been going on. Next slide, please. Wisdom throughout the building safer plants with the knowledge of the entire process. MHI, Mitsubishi Heavy Industries, leads the world in cutting-edge gas turbine development with a professional expertise of exceptional scope and depth, covering the entire plant development and production process. Here, if you go for any production unit, it may be a thermal power plant or a steel power plant or any other plant, we will have three types of information. That is the process layout, product layout, and production layout. So here, thermal in a gas turbine power plant, these three must be taken very carefully for building for the safe of the both building equipment and human beings who are all involved with that areas. For GTCC, gas turbine combined cycle, MHI exclusively undertakes the development and manufacturing work, beginning with the duct channels that hot exhaust gases from the gas turbine. This duct have the very much important role in conveying or paving the way for the hot gases after expansion in the gas turbine to the steam generation cycle. Here we have to be very much careful mm, regarding the heat loss because gases are having very much higher temperature than the ambient conditions. So as the temperature difference is there, there is a very much chances for the loss of heat from the hot gases to the environment. So if you are losing the certain heat means we are getting less production of the steam. If the production of mass flow rate of steam is less, means produced power by the steam turbine will be less. So we have to protect the heat by the application of proper thermal insulation to the duct which carry the hot gases from the gas turbine to the heat recovery steam generation boiler or heat exchanger. In next coming slides, we will discuss the uh, line diagram. From there, the hot exhaust gases travel to the heat recovery boilers that convert water into steam. Finally, the steam is used to power and a steam turbine and its associated generator. Furthermore, MHI is boosting the efforts for a safer power generation by aligning all the facilities and ensuring optimal balance, namely performing product verification via the verification facilities of GDCC gas turbine combined cycle plant-wide piping work. Here, piping work is very much important because um, every system from compressor to combustion chamber and regarding the steam cycle that conveying the steam to the steam turbine and from steam turbine to the condenser and condenser to the hot well and hot well to the uh, boiler feed pump and boiler feed pump to the uh, heat recovery steam generator line. So all these things, the pipes have to be properly welded and properly welded. And the module welding, here module welding means gas turbine blades have to be welded properly. Turbine blades will have aerodynamic structure. This aerodynamic structured turbine blades have to be welded at the root to the rotor, which is called as a turbine, and a control and a prevention. So everything will be taken into account for the safer of operation of the plant and also or the hygienic conditions of the workmen who are involving with that process. We have the knowledge of ergonomics, so we have to keep the psychological conditions of the workman and also the metallic safe conditions of the equipments. Next slide, please. Let us see the line diagram of techno-economical analysis of cycle systems. Here we are seeing certain components: compressor, combustor. I'm coming from the left to right. Compressor, combustor, turbine, HRSG. This is called as a heat recovery steam generator. And above that, we are seeing steam turbine. And after HRSG, we are seeing amine unit. And from amine unit to the stack and to the compressor and finally to the carbon dioxide sequestration. Let us discuss the one by one properly. Air from the atmosphere enters the compressor. This compressor may be centrifugal compressor or reciprocating compressor or axial compressor. But here we are using axial compressor because compressor, turbine, gas turbine and steam turbine will be mounted on the same shaft. Okay, the compressor will be absolutely driven by the gas turbine. So gas turbine has to produce more power than that of the power required to drive the compressor and come for the combustor. Natural gas, we are using natural gas as a fuel. We can use natural gas, hydrogen gas, and methane and other producer gas and super gas also. But for convenience, we are using natural gas and combustor. The combustor or combustion chamber is a chamber where that supplied fuel, natural gas, will react with the oxygen presented in the supplied air. So after the combustion process, heat will be generated. Because of that generation of heat, the temperature and pressure, temperature of the gases will be increased very much. Here, this is the constant pressure heat addition system. So whatever the pressure after the compression of the air is the maximum pressure in this, because we are adding the heat at a constant pressure. Okay, by addition of heat, the gases will have increase in temperature. So as the temperature of the gases is increasing, the enthalpy of the gases is increasing. So the gases are having much enthalpy. We can get much kinetic energy that can be converted into the useful work done. So that hot gases will enter the turbine. So here we are not seeing any nozzles. In lab, in coming slides, we will see it. Okay, the hot gases first enters the nozzles. So these nozzles convert the enthalpy drop into the kinetic energy. With that high kinetic energy, the gases flows parallel to the axis of the rotation. This is the axial turbine. Axial turbine. Turbines can be classified into three types: tangential turbine, axial turbine, and a radial turbine. Example for tangential turbine is a impulse turbine. That is a Pelton turbine, or in steam cases, D-level turbine, and radial turbine. A best example for radial turbine is Francis turbine, but here we are using axial turbine. Flow of gases what the turbine blade will be parallel to the axis of the rotation. That is why we are calling as a turbine, axial flow turbine. Very much important thing in the combustor. Let us say the here, for the proper complete combustion of the fuel, that we are making the air to have the turbulence. This turbulence help us to have the rapid combustion and the complete combustion of the fuel. Here, so we can create the turbulence by the design of certain combustion chamber. In internal combustion engine also we can have certain times swirl and squish. Uh, okay, in the combustion chamber. So what is meant by swirl and what is meant by squish in the turbulence means squish means if gases flows from outer side to the center or center to the circumference. This phenomena is called as a squish. Then what is meant by the swirling? The swirling means the flow of air perpendicular to the axis. That means this air will flows throughout the turbine blades in a circular motion. The circular motion will maybe perpendicular to the axis of the rotation. So by this we can have the rapid and fast combustion of the fuel. So once we fuel burn completely, then the entire its heating value, that is the entire heat energy will be released in the combustion chamber. So as a produced or released heat is increasing or maximum, the gases will have maximum temperature, and so it is having maximum temperature means the gases will have the enthalpy also a maximum. So we will get a maximum kinetic energy, and hence we'll get maximum rotational work, which can be uh, transferred to the shaft by the, and the generator will produce the heavy amount of electrical energy. And from that turbine, hot gases enters the heat recovery steam generator. This heat recovery steam generator is just like a boiler. This is also a one of heat exchanger. The heat recovery steam generator will contains a, a tube structure through which hot gases will flow, and over the tubes water will be presented. As the water is absorbing the heat presented in the hot gases, the water will be heated up slowly, and the formation of the steam takes places, and the produced steam will conveyed into the steam turbine. As the steam is having at a higher temperature and pressure, steam expands over the turbine blades by rotating the turbine. So as the steam turbine is rotating, being steam turbine is keyed on the same shaft, generator will rotate and power will be generated. Electricity will be generated. After this, the steam at low pressure and low temperature uh, enters the condenser. Enters the condenser. So this condenser is also a heat exchanger, which makes the steam to condense. So produced condensate or liquid will be pumped back to the heat recovery steam generator system. Here compressor, combustor and gas turbine, that is the left three parts, will come under the uh, gas turbine cycle. This gas turbine cycle nothing but Brayton cycle, and the steam turbine and the HSRG run on the Brayton cycle. So two cycles are coupled or combined to get the maximization of the produced work. By doing this cascading these temperatures, we are getting highest temperature and getting maximum power. Okay, after giving the heat to the water presented in the heat recovery steam generator, these hot gases will enter the amine unit. We are seeing amine unit. This amine unit is nothing but just like a gas treatment plant. So being these gases are produced from the combustion, they will have carbon dioxide, NOx, SOx, and um, COX. These are the emissions which may be presented in it. This amine unit will have certain scrubbers which may absorb the certain gases. So we should not discharge these gases directly into the atmosphere through the stack. Stack is nothing but a chimney. So before discharging these gases, we have to clean and we have to remove the dust, carbon dioxide, and other alkaline and solution alkaline. Okay, after free from after cleaning the gases, simply they will discharge into the atmosphere through the stack. And here we are seeing compressors. The absorbed carbon dioxide can also be used to drive the compressor. So this carbon dioxide compressor can be used to compress the air. This is very similar to the supercharging of the air. So air can be naturally aspirated or supercharged. So if air is supercharged, we will get the highest possible pressure in the turbine. So after rotating that, CO2 will be sent to the sequestration plant. What is meant by sequestration? Is nothing but absorber of the ions. Certain ions have to be removed and can be discharged into the weather. Okay, next slide, please. So here the same thing we are seeing. Whatever the description I explained, we are seeing in the slide. The NGC power plant illustrated in the previous figure is a combination of two thermodynamic cycles, Brayton cycle and the Rankine cycle we discussed, which produces the higher thermal efficiency by the combination. The Brayton cycle is an open cycle. Why we are calling it as an open cycle? We are not using the gases into the cycle. Simply, we are discharging that gases into the atmosphere. That is why we are calling them as a open cycle, and which uses the air and exhaust gases as working fluids and consists of a compressor, combustor, and turbine. The Brayton cycle is the basis of the gas turbine engine, in which ambient air is compressed and introduced to the combustor along the fuel. The fuel and air are combusted at a pressure. Hot exhaust gases flow through an expander, nothing but a turbine. A significant portion of the shaft power from the turbine is used to drive the compressor. So as already we discussed in the previous slides, so this turbine has to produce much more power than that of the required by the compressor. Then only we will get the net power output which can be used to generate the electricity. Now the compressor, turbine, and generator are typically on the same shaft and land-based heavy-duty gas turbine. So because of this, certain vibrational problems can also be minimized. Okay, the Rankine cycle is a closed cycle that uses the water and steam as a working fluid and consists of a heat recovery steam generator. Here, the Rankine cycle is closed cycle. After doing the work in steam turbine, the steam is sending to the condensing unit. That is the condenser. The condenser makes the condensation. Okay, the condensation is nothing but the steam. How this condensation is forming in the condenser means the condenser is a heat exchanger. A cooling water supplied with a cooling tower will be sprinkled or flows over the steam tower tubes through which steam is flowing. So because of the temperature difference, steam rejects the latent heat of condensation to the cooling water. So as the latent heat is rejecting to the cooling water, the steam phase will change from a vapor to liquid. This liquid is nothing but condensate, nothing but water. It will be pumped back to the hot well, and from this water will be uh, pumped back to the heat recovery steam generators, nothing but the boiler and steam. Okay, likewise, that fluid will circulate throughout the closed circuit. That is why we are calling the Rankine cycle as a closed cycle. Here, NGC systems are commonly available, and this technology is well proven. It's proved we are getting that much higher power. The pollutants from most concerned from such systems are typically NOx, that is nitrogen oxide components, and to more limited extent, carbon monoxide, MEA based COX capture system. What is meant by MEA? Monoethanol amine. Monoethanol amine. These are the, what is this formula? C2H5 C2H7NO. It's a chemical formula. So this carbon dioxide is having that components. So we have to be captured that systems by using this amine unit and the scrubbing technology, whatever we discussed in the previous slide. Okay, and discussed in the PCA design basis are proposed for the use of NGC system. What is meant by NGC system? Natural gas combined cycle system. In other words, we can say natural gas turbine combined cycle systems in order to lower the carbon dioxide emissions. By doing so, we are making our weather clean and green, and we are also reducing the global warming problem, which this global warming problem is based on because of the emissions released by the various industries. Next slide, please. Early gas turbine industry. Let us discuss let us have an information from which year we have been, people have been using gas turbine. You see, 1791. In 17th century onwards, that is early, end of the 17th century. 1791, the first patent for a gas turbine. John Gerber, United Kingdom, he had the patent on this. In 1904, unsuccessful gas turbine project done by Franz Stolz in Berlin. This is the first axial compressor. In 1906, gas turbine by Orbigard Lamel in France. He used a centrifugal compressor, but no useful power. That means whatever the power produced by the gas turbine is completely realized by the compressor for driving it. So there is a no net power. If net power is zero, no work done. In 1910, the first gas turbine featuring intermittent combustion. Holdsworth 150 kilowatt, the constant value combustion. So heat addition can also be done by constant value combustion process. This constant value combustion is invented used in 1910. In 1923, the first exhaust gas turbocharger to increase the power of the diesel engines. If you can see this, say how the exhaust gases is coming from the turbine is bestly used to heat the air. Understand? In diesel power plant, being diesel power plant will be run by the diesel cycle. So in the diesel cycle, air from the atmosphere will send to the compressor and compresses to the high pressure, and at the end of the compression stroke, fuel will be injected, and the combustion power produces like the diesel cycle functions. But here we are using the heat presented in the gas, which is coming from the gas turbine after rotating the gas turbine blades. So this heat is best used to supercharge the air. Okay, this air may be naturally aspirated air or supercharged air. If we supercharge the air before admitting into the engine cylinder for compression, the volumetric efficiency of the engine will increases. If the volumetric efficiency of the engine increases, power will be increased. So we are using the waste heat to increase the production of the power. We are maximizing the power by using the waste heat. That was they have been using right from the 1923. In 1939, world's first gas turbine power generation, drawn by every company, Nozzles and Switzerland, Olex burner, aerodynamics and Stodolala. In combustion chamber, different burners we will use. In 1935, we will use the Volax burner, which were invented in Switzerland. So from that 1939 onwards, we have been using the combined cycles for maximizing the power generation. Year by year, as the technology is improving, year by year, researchers by researchers, they have been inventing and incorporating and utilizing the best technologies to produce the high power by achieving the maximum firing temperature of the gases. Next slide, please. Okay. Installed capacity by source in India as on March 31st, 20. So this pie chart is called as a pie chart. This pie chart is giving us an information regarding the production of the power by using the various sources of energy. Here we are seeing blank. It's a coal. It's the coal-fired power station. Approximately, they produced 55.4 percentage of the total installed capacity in India. Next, large hydro and small hydro. These hydro power stations also produced 13.6 percentage of the installed capacity in India. After that, wind power, solar, biomass, the renewable energy sources, and nuclear, and gas and diesel. Being we are discussing the gas turbines, we concentrate on the power installed capacity by the gas turbines. So see, 24,955.36 megawatts. Approximately, it is contributing 6.7% of the total installed capacity by the source of in India, because by using these gas turbine cycles, we can combine this uh, cycle to any other cycle as a primary power generating cycle or secondary power generating cycle. Whatever the things it may be, our main aim is to maximize the power output, to produce the maximum of the supreme power of energy, that is electrical energy. Next slide, please. Okay, growth of installed capacity in India. This table listed the how the growth of Elk City or installed capacity in India has taken right from the 31st December of 1947 to 31st March 2019. See, there are different power sources are the thermal, nuclear, renewable sources. In thermal, coal-fired and gas-fired and diesel-fired. Of course, nuclear power also comes under thermal, but we are separately showing why means it is having that much importance. Our aim is to produce the heat by the combustion of the nuclear fertile metals. By using nuclear power, we can generate very much high, but the handling of the nuclear power, nuclear mm, fuels is very much dangerous. That is why we are using very limited. Let's come for the gas turbines, the power produced by the gas-fired power plants. It has been coming to the commission right from 31st March 1966 in India. Okay, what is the capacity in that time? Approximately 137 megawatts. So you see from that row, that is 1966 to 2019, how the production of electricity in megawatts is increasing year by year, 5 years by 5 years. 137 to in 2019 we reached 24,937. You can imagine how much power is producing by this thermal gas turbine power plants. That means people are having very much interest, and governments are also encouraging the people to install such type of gas turbine power plants wherever chances are there to combine with any other available cycles. Next slide, please. Let us see the gas turbine manufacturers. From these slides to the next three slides, we can have the certain information regarding the gas turbine manufacturers in the world. And after the fourth slide, we can see the gas turbine manufacturers in India. Let us see Ellison Engine Company and Ansaldo Energia, Avivia, Bharat Electronics Limited, Bharat Heavy Electricals Limited, and Caption Turbine, and Dosan Heavy Industries and Construction, and Gas Turbine Research Establishment, GE Aviation, Godrej and Boyce, Hanwha Aerospace, Hanwha Techwin and Hindustan Aeronautical Limited, Japanese Aero Engine Corporation, JSC Kuznetsov, United Engine Corporation, Volvo Aero, and Kaluga Turbine Plant, Kawasaki Heavy Industries, Larsen and Toubro, L&T, Man Energy Solutions, Man Turbo, Mitsubishi Heavy Industries, MTU Aero Engines, Power Machines, Proton PM, that is nothing but power machines, Reliance Group, Rolls-Royce, Dutchland, Saha, Iran Aviation, Siemens Energy sector. Next slide, please. And see these certain gas turbine manufacturers in India. BHL, Hyderabad, Siemens India, Ingenious Erectors Private Limited, NS Energy Group, Bachpan Industries India Limited, GE Power India, Mitsubishi, Hitachi Power Systems Limited. They are all the previous like this. All these are the manufacturers which are manufacturing gas turbines. These Indian-based companies are also having international clients because of their economy or personalized company financial status. They can have global tenders also, and these companies are also able to supply the required capacity gas turbines. Next slide, please. Let us see the basic structure presented in the gas turbine. Here, simply we are seeing four parts: the compressor, combustion chamber, turbine blades, and the exhaust system. So first air we are taking. This is nothing but air intake. From left side I am coming air intake. So air is entering the compressor parallel to the axis of rotation. That is why we are calling it as a axial flow compressor. As the blades are rotating over the sorry please as the blades rotating because the compressor is driven by the turbine shaft. So here work is doing on the system by the surroundings. Thermodynamics uh, point of view we can discuss. Okay, if system does the work on the surroundings, that is called as a positive work. If the surroundings does the work on the system, that is called as a negative work. Negative work is nothing but work input. So we have to minimize the work input to maximize the power output. So the turbine has to generate very much power, much power, more than that of the required by the compressor. So as the air is flowing over the blades of the turbines, compression, sorry please, compressor, the compression of air takes place. In compressor also, we have to understand two terms, stator and rotor. So as the air is passing through the small passages between these, the air will be getting compressed, okay, compressed, and hence its pressure will reaches at higher pressure that the compressed air will be enter the combustion chamber. Here we have to understand one thing. What does it mean? The as gases as the air is flowing towards the combustor right from the inlet to the exit of the compressor, it will experiences the flow of contact of the compressor. So compressor blades must be as smooth as possible because of surface roughness will causes the friction, and this friction increases the work input for compression. So it causes the increase in the heat also, which creates certain frictional problems. So row by row, the turbine blade, sorry please, compressor blades are incorporated in such a thing that the blades make the air to enter the next row of blades at a certain angle. This tip angle, this angle is called as tip angle. This angle is very much important in the point of view of aerodynamic structure or aerofoiled blades. So as air flows parallel to the shaft, row by row, it is getting compressed. is getting compressed and its pressure will increases. We know very well about the two thermodynamic properties, pressure and uh, area. So volume, if area decreases, what will happen? Volume decreases. Volume decreases means what happens? Pressure increases. Our aim is to have large or increase maximum possible pressure, highest pressure in the compressor. Okay, as the gases are leaving the compressor, it will have highest pressure. This is the maximum pressure in the cycle. With that high pressure, the gases or air will admitted into the combustion chamber. Here we have to understand or concentrate on one thing. Fuel and compressed air will be admitted together into the combustion chamber. Fuel is admitted along with the compressor to the combustion chamber. Their combustor in last slide we discussed Solex combustor like that will ignite the combustion and then combustion starts, propagates, and finishes entirely. If a fuel is completed entirely, the released heat, the heating value also maximum. If the maximum heat is generated, the gases will have highest temperature. Highest temperature makes the gases to have high enthalpies, so that higher value of kinetic energies can be generated as the gases are passing through the nozzles. Okay, so as they are producing, as flowing over the turbine blades, they will rotate the turbine blades. So blades are keyed on the rotor. So shaft will rotate and power will be generated. Here we have to, in the next slide, coming slides, we will see the entire structure of nozzles and turbine blades, guide blades, and moving blades. After rotating the turbine blades, simply the gases will leave the turbine house. Next slide, please. We are seeing one cycle. It's called as the Brayton cycle. Is the ideal cycle for gas turbine. So here you have the four processes: 1 to 2 and process 2 to 3, process 3 to 4, and process 4 to 1. Process 1 to 2 is nothing but isentropic compression, and process 2 to 3 is nothing but constant pressure heat addition, and process 3 to 4 is isentropic expansion, and process 4 to 1 is heat rejection process. Here in last slides, I discussed pressure after the compressor is the maximum pressure. Okay, in combustion chamber, temperature will increase, but pressure is constant. So, 2 P2 is equal to P3. That is a constant pressure. That is why we represent the term P is equal to constant. Here, heat is entering into the thermodynamic cycle. That means after in combustion process, heat is released and the system that the gases are acquiring highest energies. Okay, process 3 to 4 is the isentropic expansion. That means as the gases are flowing over the blades, it produces the work by the expansions. So its pressure will decreases from P3 to P4, and next the heat will be if it is an open cycle, but the gases will be discharged into the air. Process 4 to 1 is the heat rejection process. Here being it is an ideal cycle. Why we? That is why we represented straight vertical line. Process 1 to 2 and process 3 to isentropic means entropy is constant. Reversible adiabatic compression. Reversible adiabatic compression is only called as isentropic compression. Process 3 to 4 is reversible adiabatic expansion. Okay, this is also called as a frictionless. But whenever the gas or a fluid system is flowing through the solid bodies, there existing a certain friction. So entropy will not be constant because of the friction, heat will be generated. So if heat generates, definitely entropy changes. So that is why actual in actual cycle we represents point to slide away from the point two in the 2 3 line, and in the actual cycle actual expansion will be represented slightly above the point 4, and the point line 2 3 and 4 are the constant pressure heat addition and constant pressure heat rejection process. Next slide please. Inlet system, we are seeing air filter and a typical turbine inlet air cooling and gas turbine and a generator. Okay, here gas turbine inlet air cooling, gas turbine inlet air cooling. This term seems to be a certain different terms. We may create certain doubts. Are we cooling the turbines with by the supplied air? Understand? So if 100% of the air is supplied from means 25% of the air is only used for combustion of the fuel. Remaining 75% of the air will form the closed blanket over the turbine blades, because the produced higher temperature will make cause the damage of the turbine tips, the blade tips. Turbine blade tip is damaged means its tip angle will be changed. If the turbine blade tip angle changes means the direction of gas or entry of gas turbine or gases as the rows by rows will changes. So this tip clearance plays very much important. So by keeping the safe working conditions of the turbine blade tips and also certain mechanical properties, we are using the turbine inlet air cooling. Next slide please. The next compressor. Compressor used in a gas turbine is a axial flow type. Axial flow compressors are a dynamic rotating compressors that are uses arrays of fan-like aerofoils to progressively compresses the fluid. If we observe these turbine blades, which is shown in a light green color, we are seeing different rows of individual turbine blades in a radial shape mounted on the shaft. See, right from left to right, its area of cross section is decreasing. Area of cross section is decreasing. This indicates the compression of air. So compressor blades will compresses the air by doing certain work. As the air is passing through the different blades of moving blades and the fixed blades, it experiences the certain force which is compressing the air. So its pressure increases. Next slide, please. This is the axial flow compressor. In this diagram, we can clearly see the different rows of the compressor. This is the modern axial compressor. Here we are seeing stator vanes fixed to the case and rotor blades which is keyed or fixed to the rotor. So stator remains in a fixed position. Rotor blades only will rotates as the shaft is rotating. So come for the first point. Modern compressor designs are extremely efficient. The gas turbine performance rating depends greatly on the compressor efficiency, because compressor efficiency is high, then only we will get a higher compressor pressure, which plays very much important role in producing the turbine work also, because at that pressure only we are adding the heat to the gases in the combustion chamber. High performance made possible by advanced aerodynamics, coatings, and small blade tip clearances. Here we are seeing three different terminology. What does that mean? Advanced aerodynamics. Aerodynamic structure is a structure which provides zero friction, very least friction. As the fluids are passing over metallic surfaces, they will experience the certain friction because of the surface finish conditions. If the surface finish is not good, the air will experiences the experiences the friction. So this friction causes the increase in negative work or work input. So which reduces the turbine work output, net work output. So that is why the blades are in a aerodynamic structure. That the blades are also mounted or attached to the rotor in a such a direction means it changes row by row by at a designed preset angles. And coatings, these are the coatings means which helps the super finishing, so this coatings helps the air which passes with a zero friction and small blade tip clearance. What is meant by tip clearance? This is the distance between the tip of the blade and to the stator bodies. This distance will be kept least possible value, because if it is a least value, then will be much compression performance we can achieve. So compressor efficiency will be increased. Because of this, we will get maximum power. And third point, even small amounts of deposits on the compressor blades may cause large performance losses. Performance losses means work output losses, because certain deposits causes the obstruction of smooth flow of the air over the turbine blades. So it increases the work input. That is why it reduces the overall performance of the generating unit. Next slide, please. Let us come for the combustor. The combustor is just like heart of the gas turbine power plant, because here we are adding the heat to the gases. So combustor, what is meant by combustor? This is a device. This is a device which performs the complete combustion of the fuel. If the fuel burns completely, then only the calorific value or heating value or the maximum possible generation of heat will be takes place. So this generation of heat is maximum. The gases produced combustion products, that is the gases temperature will have higher values. So higher values of temperature provides the gases to acquire much value of enthalpy. Here we are seeing different cans in a rectangular box. Discontinued blue color dots are showing different cans, and the circular body. Now cursor shown by the cursor, we are seeing combustor can. See, this combustor can have small passages. These passages are meant for flow of compressed air which is coming from the air. So from this combustor, air will have the squish and swirl. Because of this turbulence, its combustion of fuel takes place. Air rapidly flows and mixes with the combustor, and complete combustion will takes places. And we are seeing multi-can combustor. By using this, we can burn maximum possible mass flow rate of the fuels. Okay, as a system, that is the combustion products are more, we can get the more power. Next slide, please. Airflow in a combustion. In this slide, we are seeing the direction of passage of air over the turbine blades. See, dark color arrow marks and light color arrow marks represents the flow of air. In combustion air, with help of the swivel vanes, flows in around the excuse me fuel nozzle and mixes with the fuel. Okay, what is the swirling? What is the swirling action and the uh, squish? Swirling means if the air flows in a circular manner over the turbine blades, that is called as a swirling motion. In this way, the air will be flows in the radial direction, which is perpendicular to the axis of the rotation, and around the fuel nozzle and mixes with the fuel. This air is called primary air and represents approximately 25% of the total air ingested by the engine. In the previous slides, I already said supplied heat. If it is 100% air we supply, among that 25% of air, 25% of air is absolutely meant for production of the uh, gases by the combustion, and remaining 75% of air is used to form an air blanket around the burning gases and to the lowering the temperature pickup by keeping the safe thermomechanical properties of the plate tips and as well as metallic structures. Next slide, please. The turbine. The turbine are two types: radial and axial. What is the how we can say the so and so turbine is a radial? If a system or a working fluid is entering the turbine in radial direction, that is called as a radial turbine. Working fluid enters the turbine parallel to the axis of rotation, that is called as axial turbine. Like the compressor, turbine expansion takes place in stages. What is meant by a stage? A row of stationary blades followed by the row of moving blades. Combination of these two is called as a one stage. Next slide, please. You are seeing two-stage axial turbines. In left side, we are seeing rotor blades, and right side, we are seeing nozzle blades. Now, from bottom of these nozzles, yes, we are locating that area with the help of cursor. Okay, we are seeing certain red tips. What is the why we are showing that the tips with the red color means nozzle ends or tips are experiencing with the highest gas firing temperatures, turbine inlet temperature. That is why nozzles are appearing at a reddish condition. That highest possible gas firing temperatures are possible. Researches are going on to improve this 1500 degrees centigrade firing temperature to 2000 also. Turbine modules. The axial flow of turbine consists of gas of stages, each made up primarily of a set of stationary vanes followed by a row of rotating blades. Typical modern aircraft gas turbine blades have both impulse and reaction section. We are seeing the two different terms, impulse and reaction. Based on these impulse and reaction, we are classifying certain turbine is impulse turbine and certain turbine is a reaction turbine. What is meant by impulse? The impulse is nothing but the force acted upon a body for a short time interval. That is called impulse. Best example for impulse turbine is D-level turbine in a steam side and Pelton turbine in the hydraulic side. And reaction, what is meant by reaction? It is a pressure difference. The pressure difference between the inlet and outlet are called as a reaction pressure. This reaction pressure is the basic source for the creation of driving force among the turbines. That is why we are calling them as a reaction turbines, reaction pressure turbines. Okay. Exhaust system. The exhaust system is a very important system which performs the four functions. It must reduce the noise to the atmosphere, hot gases away from the personnel, and it minimizes the back pressure to the gas turbines. What is meant by the back pressure? The back pressure is nothing but pressure at which gases are leaving the turbines. So from highest pressure, if we are keeping least back pressure means we are making the gases to expand furthermore in the gas turbine unit. So if the gases are expanding furthermore means producing rotational work or turbine work is improving. That system we have to achieved by the proper exhaust system, because the exhaust system have to receive the exhaust gases at the least possible pressures also, and mechanically well during extreme temperature changes depending upon the peak load conditions, uh, that gas turbine units may run for a high demand also. So at that also this gas exhaust system have to be well suited to accommodate such higher temperatures. Okay, next, there are certain types of turbines: shaft power gas turbines and jet engines. Shaft power gas engines is absolutely meant to produce the shaft power. These shaft power uh, gas turbines is used for generation of electricity only. Jet engine gas turbines. It is a gas turbine whose goal is mainly to produce the thrust. What is meant by the thrust? Nothing but force. If the thrust, we are seeing uh, aircrafts or jet engines and rockets as the combustion products through the nozzle, which may issues from the uh, that aero engines or jet engines or rocket engines with high thrust. As per the Newton's third law, every action has equivalent opposite reaction. If the thrust is much more, so the vehicle, or it may be a jet or a rocket, moves in the opposite direction with the same force. Okay, next slide, please. For the plant applications, gas turbines can also be used, classified as cogeneration. Cogeneration means combined generation power plant. The gas turbines combines can be combined with steam turbines, can be combined with diesel power plants, can also be combined with steel industries, because to get to the molten metal we must need the heat. So by using the blast furnace we can generate that heat by the combustion of the fuels. So that blast furnace gases can also be used to rotate the gas turbines. So by using that waste heat we can produce the much maximum power. And next, combined cycle power plant, and also we can combine this cycle with the Rankine cycle, that is steam power plant. That means in steam power plant, as already we discussed in the previous slides, gas turbine exhaust will be best used to generate the steam. And see the cogeneration power plant. Here we are seeing H25 power output, 40,500 kilowatt, overall efficiency more than 80%. Here, what is meant by H25? H is nothing but heat rate. Heat rate is nothing but the heat utilized to generate 1 kilowatt power. So, by using this cogeneration power plants with help of gas turbines, we can get 40,500 kilowatts. Overall efficiency more than 800. Okay, let us discuss the performance variables. Performance variables plays very important role in the maximization of the performance of the gas turbine. What are there are certain factors: environmental factors, material factors, operation factors, type of fuel using, and the exhaust temperature. The environmental variable means ambient air, ambient pressure, and relative humidity. Humidity plays very important. What is meant by humidity? The amount of water vapor presented in the air. So, so this and relative humidity means it is the ratio of actual water amount, water vapor amount to the maximum possible amount of water vapor that could be achieved at that temperature. It is called as a relative humidity. If you see the effect of ambient conditions on the production of the gas turbines, and design and manufacturing of the gas turbine. And X-axis we represented the temperatures, and on y-axis we represented the percentage of the complication of the design and the production of the gas turbines. So if temperature, ambient temperature is more than 16 bar 16, that is from 16 to 49 degrees C, design complication will have very less complications. Whereas the temperature is decreasing, design will become very complicated. So we have to have the ambient conditions which may shoot to the best possible generation of the power. Ambient pressure, this is the pressure of air at which air is aspirating or coming from the either turbocharger or the nature. So air density reduces as the site elevation increases, result the airflow and output decreases. Next slide please. How the output decreases means it takes the much power for the compressing the density air. Here we are seeing certain graph which represents the power output percent and the produced heat energy. Power output is percent represented on x-axis, on y-axis heating value represented. Say LHV. What is meant by LHV? Lower heating value. This is also called as lower calorific value. Lower calorific value. What is meant by calorific value? It's nothing but heat generated by the combustion of that particular fuel. So then what is meant by LHV? That is lower heating value and high heating value. Mostly we are using fossil fuels. The fossil fuels will contain oxygen, hydrogen components. This hydrogen components, while it is reacting with the oxygen presented in the supplied air, it will forms the water vapor. Because of the generation of heat in the combustion chamber, this water liquid or water become the steam. So water is becoming the steam means it is acquiring certain heat in the form of latent heat of vaporization. So this heat is, if we account such type of heat plus LHV, lower heating value. So the total summation is called as high heating value. So high heating value is equal to lower heating value plus the heat presented in the steam, which may carry along with the exhaust gases. This heat presented in the exhaust gases acquired in the form of latent heat by the steam cannot be condensed. That is why we are representing lower heating value only. Lower heating value is the heat which can be utilized to generating the power and which can be extracted after the expansion of the gases in the gas turbine. Fuel heating. Before admitting the fuel into the combustion chamber, we have to heat the fuel. Understand, there is a reversible mixing and irreversible mixing. We know those two terms. What is meant by reversible mixing? If hot fluid mixes with hot fluid and cold fluid mixes with cold fluid, these two are called as reversible mixing. If cold fluid mixes with hot fluid, that is called as irreversible mixing. This irreversible mixing decreases the amount of heat generated in the combustion chamber. So to avoid the certain heat losses and irreversible mixing, we have to heat the fuel before admitting the fuel along with the compressed air into the combustion chamber. So from where we are getting this heat from the feed water in the combined cycle, the feed water which is coming from the economizer, the heat will be used to heat the fuel before admitting into the combustion chamber. Because of this, what happened? Combustion chamber temperature increases, best possible combustion takes places, high value of maximum possible generation of heat takes places so that we can achieve highest combustion efficiency. The source of heat from the fuel is typically from feed water. Since use of this energy in the gas turbine fuel, heating system is thermodynamically advantageous because by using this heat from the feed water, by using method of fuel heating, we will increases the combined efficiency by 0.6%. And also these gas turbines can be used for base load applications, peak load applications, and standby applications. Base load means this is the load used by the people, which is the constant. Peak load means this is the maximum consumption of the customers, industries, uh, depending upon the demand. So if the base load is always constant, but the peak load may be increase or decrease depending upon the demand by the customers. So this gas turbine power plants can be able to withstand to the supply the base load demands and the peak load demands, and also the standby units. There are certain advantages of the gas turbines. Is having very high power to weight ratio, and it moves in one direction only, so vibrations are very much less. Fewer moving parts are there, so friction problems are less, so lubricating cost and maintenance cost is less. Big gas turbines can achieve the highest temperature exhaust stream that is very useful for boiling water in a combined cycle. Low operating pressures. There is so explosion problems are also less. High operation speeds and low lubricating oil cost and consumption because of the less moving parts. There are certain disadvantages with this, because every system will have both advantages and disadvantages. As a engineer, we have to maximize the advantages and minimize the disadvantages. So cost is much greater than similar size reciprocating engine, and machining operations are such a complex one, and a longer startup than reciprocating engines. Delayed response to the changes in power setting. These are the disadvantages. Next slide, please. Applications. We can use these gas turbines for electric power generation and industrial uses, and for marine propulsion. But we can run these gas turbines to run the ships. Okay. And job opportunities. The engineers, we can have the job opportunities in the gas turbine phase. Power plant gas turbine operation, maintenance, and gas turbine fluid system process engineers and project managers, and gas turbine operation engineers, quality assurance and quality control supervisor, and control and instrumentation engineer, and senior developer and engineers. Next slide, please. The gas turbine technologies for future. In developing large capacity gas turbines as the main machines in combined cycle power plants, Mitsubishi Heavy Industries has been making every effort to increase their thermal efficiency. Right from the 1980s, when commercial operation of power generation plants with a combustion temperature 1100 degrees centigrade began, combustion temperatures have been increased at a rate of approximately 20 degrees centigrade per year, and now it reaches to the 15 degrees centigrade. However, further increases come up against a number of technical issues, including reducing NOx emissions and the need for higher strength materials. At the same time, the period of high economic growth in which specified increase in demand for power would be expected has come to an end. Now, new products see increase cycle temperature. We are trying very much to increase the cycle temperature by using the two different cycles. According to the second law of thermodynamics, when the maximum temperature of thermodynamic cycle is raised, the efficiency of energy conversion is increased. It is an ideal combination in which the gas turbine uses high temperature heat energy at 1100 degrees centigrade, while the steam turbine recovers the power from low temperature heat energy at 600 degrees or less. By using heat cascades in the combination of these two temperature ranges, thermal efficiency can be increased more in combined cycles than in simple cycles. This graph represents turbine inlet temperature, represents on X-axis 1000, 1500, and 2000 can also be achieved. And x-axis 40, 50, 60 represented the lower heating values, that is thermal efficiency represents. So if we achieve 1600, 17 degrees, 1700 centigrades C class turbines, we can achieve the highest possible combined efficiency, 60%. There is a fuel flexibility with help of gas turbine technologies. Concentrate on the figure. Okay, here we are seeing some hydraulic power, nuclear power, coal, and the LNG, liquid nitrogen gas, and oil. See, if you see this power generation, fuel sources, peak power peak power demand can be generated with help of the gas turbines. So these gas turbines can be suited for the large capacity base load and the middle range capacity peak loads and highest possible peak loads. So as well as natural gas, the gas turbines have been fueled using excess refinery gases and gas from ironworks or blast furnaces. In the steel industries, these blast furnaces gases will plays very much important role after producing the molten metal. So turbine, um, say, in future, the use of excess gas is expected to expand. Around 40% of Japanese coal imports, including that used for manufacturing coke, is consumed in ironworks. The gas is produced from the other methods like gasification, coke oven gases, and as producer gases can also be used to drive the compressors. Next slide, please. Peak power generation. Concentrate on this line diagram. Here we are seeing SOFC. SOFC. This is a solid oxide fuel cell. Solid oxide fuel cell. This is a fuel cell is coupled to the inverter. Understand? By using that, the fuel cell will generate the DC power. From this DC power can be converted into the alternating current. Okay, so the certain heat which generates in a fuel cell can also use it to heat the natural gas before admitting into the combustion chamber. That means we can combine this gas turbine to the any other possible secondary power generation unit. By doing so, we can achieve certain highest possible power, 500 megawatts. Next slide, please. These are the new cycles. Okay, future is waiting. We are all expecting the new cycles in coming days because most of the eminent personalities are doing researches on producing the highest possible gas firing temperatures from 2000 degrees to 2500 degrees. There are very much technological issues that have to be solved in combining the coming days. Ultra high energy conversion. In coming days, we can have the ultra high energy conversion, which provides the 2000 to 2500 degree centigrade firing temperature. So finally, I come to the conclusion. In this analysis, the 2 points concerning the fuel flexibility and intermediate capacity peak power generation were cited near future trends, while the 2 points concerning further increase in the combustion temperature of gas turbines and challenges to a new cycles were cited as mid and long-term trends. In recovering energy obtained from fossil fuels, it is important to efficiently convert the thermal energy of the fossil fuels with a maximum combustion temperature of 2000 degrees to 2500 degrees centigrade to the electric power through cascading achieved by the combining the cycles. The means of accomplishing this goal includes increasing the maximum temperature of the present 1500 degrees centigrade gas turbines, achieving new cycle to recover thermal energy at 2000 degrees centigrade level by other methods, and developing a combined cycle to recover the thermal energy without combustion, such as fuel cell system. In the last slide, we discussed it. Next slide, please. In third conclusion, in any event, gas turbines are very effective machines for efficiently converting temperature 1100 degrees centigrade to 1500 degrees centigrade or higher the large scale, and it can be safely be said that in the examination of various cycles, gas turbines will play an important role as an effective means of converting combustion energy in the future. Any queries, please? You can ask me any question. Any question? Thank you very much. Lastly, I'm very much thankful to Almighty God and our management and the principal and other faculty members and respective HODs of departments and all the students and viewers from other places and other college students and other college faculty also. I'm very much thankful to you one and all. Keep, keep in touch with the DBS talks. You can have very much knowledge through this DBS talks. Our management has taken very much initiative step to bring the knowledge to all the corners of the people who are watching to the through this YouTube. Thanking you one and all.